AI is everywhere. It models plasma turbulence in real time to maintain stability in nuclear fusion reactors. Clinicians employ it to aid in the diagnosis of tumors and diabetic retinopathy. It analyzes satellite imagery to help archaeologists identify the sites of ancient ruins. If you've ever wondered how AI works, you're in the right place. Welcome to the Data and the Story, where we deploy curiosity as our defense and offense in a fast-changing world. I'm CJ Washington. This is the second in a series of 5 primers that explores how AI learns. Many Data in the Story episodes, from autonomous vehicles to the water crisis, will touch on AI. And to better focus on the big picture, I'll send viewers here for the details about how AI works. The first primer covered artificial neural networks, comparing and contrasting them to the human brain. If you haven't watched it yet and you're new to AI, I suggest watching it now. It provides the foundation for understanding this primer, which is all about supervised learning, learning from labeled datasets. The next 3 primers will cover unsupervised learning, reinforcement learning, and large language models. You might have heard of linear regression, decision trees, or support vector machines. They all use supervised learning. We will focus on deep learning, neural networks, and continue with our prediction of the probability that a video was generated by AI. To train our artificial neural network, we'll need training data. And by training data, I mean labeled data. Recall that each video is represented by a vector. Each vector contains features extracted from the video: blink rate, speech error rate, sync delay, rate of micro-involuntary head movements, and video category: education, news, or comedy. The higher the quality of our data set, the better our algorithm will perform. What do I mean by quality? First, and it probably goes without saying, we need correctly labeled data. We also want a balance of positive and negative examples, meaning we want our neural network to see many examples of videos generated by AI and many examples of videos not generated by AI. As a data scientist, unbalanced data sets is one of the most common obstacles I face. Say 90% of the videos in our data set are not AI generated. That's good if we're pro-human produced content, but it also means that our neural network could be correct 90% of the time just by guessing that every video is not AI generated. That isn't the type of learning we want. For this reason, we typically look beyond simple accuracy metrics to evaluate a model, and there are adjustments we can make to compensate for an unbalanced dataset, but they're beyond the scope of this primer. We also want real-world diversity within our datasets. There's a famous cautionary tale in the ML world about the husky versus wolf classifier. The model looked impressively accurate, but it was discovered that the model hadn't learned anything at all about the appearance of the animals. Because most of the images of wolves tended to have snow in the background, it learned to identify snow with wolves and lack of snow with huskies. This is an example of overfitting, where the model memorizes unintended patterns in the training data instead of learning the real concept. For our toy problem, we want to make sure that our training set includes videos generated by various AI platforms. If all of the AI videos in our training set are generated by Google's VO, it might learn patterns unique to VO and totally miss videos generated by Luma Dream Machine. Insufficient labeled data is also a common problem, but not for us. We have an untrained neural network and a data set containing information about 1,000 videos. I made that number up to ensure we have plenty of data for our toy problem. To solve a problem like this in the real world, we will want to start with at least 10,000 labeled videos, and instead of using our domain knowledge to select features, we would feed the images directly to the neural network and allow it to discover or learn the most meaningful features. The process of discovering the optimal way to represent the data is called representation learning. The simplicity of our toy example will make it easier for us to interrogate how supervised learning works. The weights and biases in our neural network have been randomly initialized. Remember, the weights and biases, collectively known as parameters, store knowledge, so our neural network currently knows nothing about our problem. It's ready to learn. We feed the 7 features from our first video into the network. The data is multiplied by weights, and a bias value is added. This total is then transformed by an activation function within the neuron. In our example, we are using rectified linear units, ReLU, which outputs a 0 if the input is 0 or negative, or the input value itself if it is positive. This happens at each layer. At the output layer, the network makes a prediction. Instead of ReLU, the output neurons apply Softmax, which ensures the output sums to 1. Because the weights were initially randomized, this is just a guess. To improve, we compare the initial guesses to the labels using a loss function. If we feed our neural network a batch of 100 videos, the loss function will calculate the distance between the model's guesses and the truth according to the labels. To shorten this distance, we use backpropagation. The end result of backpropagation and optimization is adjusted weights and biases that align the neural network's predictions with the label training data. Backpropagation calculates the gradient, a mathematical map showing which direction each weight needs to move in order to reduce the error. It essentially assigns blame to every connection in the network. Then, an optimizer nudges those weights downhill toward a lower loss. This collective shift across thousands of weights is what we ultimately call learning. If backpropagation, gradients, and mathematical maps are confusing, that's okay. There are 3 main takeaways from this primer. 1. Untrained neural networks begin with randomized weights. 2. Neural networks learn by processing data, making predictions, comparing their predictions against labels, and then adjusting their weights to align their predictions with the labeled data. 3. Neural networks don't inherently understand the concepts we want them to learn. They simply identify patterns that optimize their loss function. It's the ML engineer's job to design the data, training protocol, and evaluation metrics such that the model learns the right patterns rather than unintended noise. If you want to dive into the math of AI, and you want an entertaining book to guide you, I recommend Why Machines Learn by Anil and Nathaswamy. I discussed the book in detail in the primer on neural networks and shared some important caveats before reading it. You'll find a link to the book in the description. The toy example we used included label data for 1,000 videos. You're probably wondering, who is going to label all that data? It's a great question. I don't have an answer, but I do have a recommendation. Unsupervised learning. The beauty is that labels are not required. Let's get into that in the next primer. Keep your curiosity strong, and whatever you're curious about, I hope it leads you back here, and I hope you find what you're looking for. Do you wonder how unsupervised learning works? Or maybe you're asking, what is unsupervised learning? Subscribe, turn on notifications, it's coming to the data in the story.